So what we've been talking about, if I run this maybe at 10 speed, is we've been trying to make this distinction between how fluids travel when they're separate phases. And we've talked about the mechanisms by which that occurs. And it relies on two basic pieces of understanding. One relates to these capillary pressure versus saturation curves shown on the top, which define the pressures you have to apply to physically push fluids into the subsurface at some equilibrium distribution. And the second one is relative permeability curves, which say how it might move in the subsurface. And so the motion conforms to Darcy's law. We just have to define it in a specific way. And that specific way is in defining a relative permeability, which is just a number between 1 and 0, which really says what proportion of the cross-sectional area of the flow system is open to fluid 1 and what proportion is open to fluid 2. And that proportion changes as you get more of one fluid versus the other one. And so the relative permeability curve is basically something that describes that process so that we can use Darcy's law to say something about how these fluids will separately move in the subsurface. And we spent some time talking about that. And the different stages on the relative permeability chart you see there conform to different saturations. 100% water saturation to the right, 0% to the left. And as you exchange water for something, that something has to take up the remainder so that the sum of the two saturations add to 100%. And so in applying it, it's really just applying Darcy's law, but applying it really with the green and the red flow portions separated out as separate cross-sectional areas of flow. You could think of it just as that. And so this relative permeability curve is really just a manifestation of the fact that the cross-sectional areas change as you get different saturations, and therefore the relative permeabilities change. They don't quite look like these X-plots because the non-wetting fluid tends to take care of the biggest pore spaces first, just in the wetting, and the wetting fluid, the red fluid in this particular case, forms on the boundaries of the particles, and so they form in different ways, and so that's the reason that the relative permeability curve isn't an X curve but has some structure to it, and it revolves around the saturations. So that's the reasons why these curves don't quite add to 1. If you look at this magnitude here, this magnitude here is the sum of the two curves, and it clearly isn't 1. The curves have hysteresis in them because wetting and non-wetting behaviors are different depending on the sequence in which it goes through. And we can also use this idea of capillary tubes, which we've used for porous media, to represent the behavior of fractures. So we've always made the case that fractures are quite open. They're easy conduits for stuff to flow down. And in the same way we could look at the capillary tubes to define flow in these systems, we can look at parallel plates and flow between them to look at the standard conduit, if you like, that represents a single fracture. And if we do that, we can come up with an expression that allows us to say something about the permeability of fractured media, which basically tells us that permeability we can define as a magnitude which is equal to the cube of the aperture, like a diameter, and the spacing between the fractures. And we rarely use that in that form because we can't really measure this very well to be able to get a magnitude of permeability. But what we can do is we could write this as b cubed is equal to the cube root, or 12 spacing times k. Take the cube root of each side and get some equivalent aperture out of it. And if we're able to get an aperture out of this, which represents the same as a pore throat diameter, then one thing you could use is, for instance, use permeability to calculate what the capillary characteristics are in your system. And that's exactly what's going on here. To be able to define the capillary characteristics, and it'll come to some equilibrium in a minute. And I'm going to halt it. And so if you look at flow in a tube, and if you look at the capillary characteristics of that tube, you can relate the height rise in the tube to the diameter. You can also relate the flow within a pipe to the diameter of the pipe. And those are the expressions that are given here for a permeability related to the diameter of the pipe and the porosity, and the capillary characteristics in terms of the capillary pressure or the height rise in the tube as a function of interfacial tension and diameter. So if you take this expression and write them both in terms of the diameter of the tube, which is here, and then you equate those diameters of the tubes, you get a very interesting expression, which is that you can relate interfacial tension, capillary pressure, permeability, and the porosity together. And if you rearrange that, you will see what else. Let it run a few seconds more. It will run. Okay. That's exactly the expression we need. And so if you take that expression and you rearrange it in terms of the parameters that are there, so I could rewrite that expression as 4 divided by square root 96 is equal to capillary pressure. I suppose I could write it on the screen as well, but I can't overwrite it on the video, multiplied by K porosity and permeability. And so this comes from taking a tube to look at the height rise in the tube as a capillary tube. It takes a tube looking at the transmission of fluid along that tube as a pipe to be able to define a permeability as a function of tube diameter and the porosity of the porous medium, or the average pore diameter in the system. And coming out of this is something that gives you, this is about 10, right? This is 4. And so this is a manifestation of something that we've never described, but is a standard result, is that if you look at the capillary versus saturation curve, for the saturation of water from 0 to 1, and you plot this as the J function, this intercept here, which is right behind me, is about 0.3. And that's exactly where it comes from, right? This is, if this is 0.4, if this is 0.3, that's exactly where this relationship comes from. And so the idea is that if you use these component features for porous media, it's tubes to look at capillary height rise and to look at transmission to get Darcy's law. For fractures, you can get a height rise in 2 parallel plates, and you can also get the transmission between 2 parallel plates, and you can come up with some relationship. But the most important relationship here is that in some way we can describe this bubbling pressure, PC0 as we've called it, from this. And the other thing I suppose that we could write from this is that we know that capillary pressures in some way are proportional to interfacial tension and porosity and permeability squared. And so there's a relationship between them. And the reason there's a relationship between them is that we're using the same characteristic conduits, one for looking at height rise in a capillary, one for looking flow in a tube. They have a single length dimension attached to them, which is either the diameter or the aperture between the 2 plates. And as a result of that, we can link capillary behavior and flow permeability behavior to each other because they both depend on that characteristic feature, I guess. All right, let me put it back at 10 speed. Just see the rest of this developing. What else do I want to say as we go through this? Yeah, well, I'm making exactly the same point that I just said. This is the 0.3 you see on the right-hand side. It's actually 0.3 something, right? Not 0.3 exactly. Capillary pressures are proportional to 1 over permeabilities, square root. And then if we combine these behaviors, So we have Darcy's law and flow behavior. We have the capillary response, which says what the equilibrium saturation should be at any particular capillary pressure. We can combine these in a conservation of mass equation. And we end up with a conservation of mass equation for fluid 1, a conservation of mass equation for fluid 2. Those are the two equations that are written down there at mid-height on this slide. Net accumulation of fluid 1, transmission of fluid 1, net accumulation of fluid 2 equals transmission of fluid 2 in or out. You've seen that before. Don't need to dwell on the form of those. The second equation is that the saturations have to add up to 1, and the pressure differences between the two fluids have to satisfy the capillary pressure curve. So there are 4 equations we have, and we have 4 unknowns. We have a saturation of fluid 1, saturation of fluid 2, pressure of fluid 1, and pressure of fluid 2. We can solve it, and if we solve it, we end up with a solution which allows us, for instance, to look at having an oil-filled reservoir that you want to get the oil out of it. How do you do it? You suck the oil out? Not so well, but you can push water in under pressure to push the oil out. And so you could think about trying to push the oil out by physically introducing fluid into the bottom of a reservoir and physically displacing the oil up through the system as a tongue, this purple tongue that it moves through here. And there are solutions available that allow us to do that. And so that was kind of the recap of exactly what that was doing. And it's finished. So that's it. So up to now, we've talked about capillary pressure, saturation curves, and permeability. And so what we'll try and do today is look in a bit of a more pragmatic sense, maybe. Not so many equations, but to look at physical behaviors that we'd expect to see in these systems and how we might go about measuring some of those behaviors. Okay. So we'll talk principally about the movement of NAPLs, both denser and lighter than water, and look in overview about this progression of fluids as it conforms to these two major equations that we have. Capillary pressure versus saturation equations, which define the equilibrium pressure distribution and the saturations in the system, and Darcy's law, which says how quickly the fluids move in the subsurface. Don't want to talk about that. Don't want to talk about that. Maybe do talk about this now. So talk about, in a physical sense, what's going on here. So we've talked about multiphase flow. We kind of term it generically as multiphase flow because the individual phases could be many. There could be 3 phases are present in our system. For instance, in the vadose zone, where we have air-filled pores with a bit of water at the grain-grain contacts, if you spill a oil through that, you'll have 3 fluids in the system at one time, and they'll behave in some way. And so we can label the fluids. All that matters about the fluids is whether they're wetting or non-wetting as to how they might behave. And that describes exactly what the system is, how the system behaves. The simplest system above the water table would be to look at behavior in the vadose zone. And of course, the vadose zone is the part that has to be transited if you spill something from the surface for it to get to the water table and then be carried away by the fluids that are traveling below the water table. And so the one way to think about that is to look at our geometry that we've already talked about. This would be the water table at some depth. And if we were, for instance, to plot pressures above that water table, bless you, with depth, we've always done Z as positive upwards pressure. Then we know that the distribution of fluid pressures would be something like this. This is change in elevation. This is the change in pressure. We know that this is equal to rho g. And so we know the orientation of this. If I do this down here, just finish this off, I guess. So as we go down below the water table, just like in the swimming pool, we feel the pressures build up and it conforms to the unit weight of the fluid. If we go above that, exactly the same occurs. So as we go up from the water table here in the capillary fringe, then what we expect to see is that if we would cut off the fringe at this point here and try and hold the water up by its bootstraps, so to speak, then the pressure that we'd have to apply to hold it there would be equal to this amount here. Is it on the figure? Yeah, it is on the figure. And so this would be the pressure that we'd have to apply. And this is often referred to as the tension saturated zone. I guess just to back up a little bit, it's not by coincidence that this curve that we're looking at here happens to look at least a little bit like didn't want a straight line. Whoops. Didn't want to do that either. If we draw both of these, right? Capillary pressure, which is the difference between non-wetting and wetting pressure and the saturation of water. It's no surprise that this curve looks a bit like this. This is saturation at 100%. This is saturation at 0%. And this really is our idea that this is, so this would be the height where PC0 exists. So this would be PC0. This magnitude here. And as we go up from this, because we go further up on this curve here, then the saturations begin to change. And if we draw out exactly what those would look like, then this would be the saturation of water. And this would be, in this particular case, the saturation of the non-wetting phase, which is a saturation of air. So this is air and water, nothing more than that. And so these conform to the irreducible saturations here. So we're not saying anything new from what we've talked about before. So this would be the irreducible saturation of water. This is the maximum amount of water, the minimum amount of water we can have in, or the maximum amount of air we can get in, sometimes referred to the residual saturation of water in this particular case. And this would be the residual saturation of air. So that's the geometry, if you like, by which this would occur. We know how we can get these magnitudes. We know that the HC0, it should be up on the board somewhere, or perhaps it wasn't on the board, is going to be equal to, 4 times interfacial tension divided by the pore diameter, something like that. Right? And we can convert that to a pressure by multiplying through by unit weight. PC0, I think that's right. So if you reduce this, then this becomes larger. Yeah, so it is. It's that ratio. And so we can get this magnitude from the grain sizes. And so our interest in this, and perhaps surprisingly, is that this capillary fringe is going to be largest in very fine grained materials. So in clays and silts, this will be high. In sands and gravels, it will also be almost be 0. If we know what the grain sizes of these components would be and their interfacial tension, we could calculate exactly what the height of this capillary fringe would be. And so we haven't put it on here, but this height here would be what we've called HC0. So hopefully this is all starting to make some sense. And we used that before. We spent a fair amount of time, if I zoom back from this, to be able to explain exactly how this works when we looked at saturation distributions. I think it was before this, right? Oh, why can't I find it? you know, it's the horizontal slide that has the spill distributions on it. Perhaps I'm not going to be able to find it. Maybe I'm not. I can't, so I won't look for it anymore. But we can define this behavior. We made these, the point, I guess, was that above the Vadot zone, if you look at the density, the unit weight of air, which almost is 1,000th that of water, then the capillary pressure is really just the difference between these two curves. In other words, on this, the capillary pressure would just be this magnitude here. PC is equal to the pressure in the non-wetting fluid minus the pressure in the wetting fluid. The non-wetting, this here is water, and it would be a negative pressure, right? It's in tension. So this would be a negative pressure, which is negative, which is a positive, and this would be a small negative pressure, so the capillary pressure would be a positive value. And it's just the difference between these two. And I guess it would be more obvious if you extended this a little bit further up. So the capillary pressure, just to make clear, is this magnitude between these two, not all the way to the axis, not including this part. And that defines our saturation. So that was the basis why we could, in that previous figure, which had these two panels, one on either side, on the left-hand side it was looking at saturation distributions above the water table, and the right-hand side was looking at saturation distributions below the water table for DNAPLs. And so we can apply the same kinds of ideas to if you had a spill from the surface, but now the difference was present in the other case. Now the difference is we potentially have three fluids. And so we start off in this case. This is a time sequence that looks at times of initially, after 2 hours, after 8 hours, and final conditions. It defines these figures that are a height above the water table. So this is the water table that's present here. And this would be our elevation Z, which is positive upwards. It defines a water content. And so we defined before that the saturation is equal to the volume of the fluid divided by the volume of the voids. We also know that the porosity is equal to the volume of the voids divided by the total volume. We defined these maybe on the second day that we met. And I only say this to note that the water content is defined as a volumetric water content. So this is volumetric. And let's call it little lowercase w, which is the volume of the fluid, not defined as a function of the volume of the voids, but of the total volume. And so, in other words, 40% moisture content, if that fills all of the voids, that means it's the same as the porosity. So in other words, if you fill all the voids with fluids, so this is VF, then the maximum value of the moisture content can be the porosity. And so in this particular case, this is the porosity. And I suppose what you could also do is you could scale this so that this was a saturation of 0. And this was a saturation of 100%. Right? So just a different. So in other words, this would be from here to here would be all the full saturation of the system. So this means that this is just scaled in a different way. So and this is used by soil scientists and agronomists, they usually work in terms of volumetric moisture content rather than saturations, just by historical reasons. And so this looks a bit like a capillary pressure versus saturation curve. So this would be the imposition curve, right? So I'm going to draw this, but I'm going to scrub it out. So the other curve would look like this. You could imagine. And I'm going to get rid of that. And so this is really the imposition curve. And what it represents are, this would be the amount of water that's present. This would be the amount of air that's present in terms of proportions. And nothing else is done yet. So now we're going to put some stuff in here through the top. And it's going to be oil. We're at 0 seconds. And so what happens is that you can imagine you're dumping this into the subsurface. You have this plug that's going to attempt to move downwards. And so now, if you look in the system and you choose a particular depth, this is the amount of the proportion which is oil. If I keep the same colors the same, this is the amount which is air. And this is the amount which is water. And so what really we have going on, I guess I won't do it while is that we have this tongue, if you like, of this other fluid, and its physical manifestation is to be here, with this little piece that goes down here. And it's slowly penetrating as a slug as it goes down into the ground. The capillary forces aren't in balance, it's out of equilibrium, so it keeps on traveling. So if we look after 2 hours, we look at 8 hours. I could make it so you can see all of these things at the same time. It's traversed so that it's now gone down, and it's now started to rest on the water table. So this originally was, this region here is the capillary fringe. This is the tension saturated zone here. So up to here it's almost 100% saturated with water, except for the residual amount of air that's present, maybe as a bubble within the center of the saturation. So you remember that we drew these before. If we have some grains, bad choice of colors, and I don't want to over-explain this. If we have some grains that are present within here, then we said that the non-wetting fluid, which could be air, I suppose, would be present as a small bubble in here. And the rest of this fluid would be water. The rest of the fluid filling this place would be water. So this would be a bubble that would be pushed in, and it gets pushed in right as you get to this point here. And so it's this amount here is containing the stuff you can't get in, and now as you add some more air to the system, more air goes into it. So now this tongue has come down. It's resting now. It's buoyed, if you like, by the fact that it's resting on the system. It's lighter than water. Talking about LNAPLs first. And again, if you look across here and you choose a particular line to do this across, then you'll see that the air takes up this portion. The oil takes up this portion, and the water retreats in the remaining place, which is here. And so, as you allow that to keep on going, then this is really the water table. It's like the water sitting on top of a swimming pool, oil on top of a swimming pool, or your salad dressing bottle. It comes to some final equilibrium, and then I guess that's the most interesting one, because this corresponds to what we'd expect to see within our system that we've drawn so many times. And so in our particular system now, there's a little bit of air that's present at the interface. There's a lot of oil exists at this level, and there's a little bit of water that is present here. Whoops. I won't change the colors, but you get the picture. So, no. And so, in some sense, it's not very different from what we've been trying to draw all this time. And that has been a water table. Looks like this. A kind of chimney of this stuff here. A big lens of this stuff that's present within our system. And the other parts of this. And so that's exactly what we have, right? This is the water table. It's buoying this up, cushioning this stuff that's flown down through here. If we look at the saturation of oil in this particular part, it's not very high. It's something like this. So in terms of saturation, if this is 100% down here, and this is 0, then this looks like it's a saturation of oil is about 5%. Water, so oil is about 5%. Water, I don't know, is about 2%. And so that would mean that the air is something like 93%, because they all have to sum up to 100. And if we look down further here, then what do we have? In the same order, the oil is something like, I don't know, it's about 70%, I could imagine. The water is more, because you've compressed the water table. Maybe that's 20%. And maybe the air, I mean, these are just numbers that don't make any difference. The air is 10%. And the only thing I know is that they should sum up to 100% again. But that physically is a description, as we go down through the vertical column, what the saturations would look like to the different components. And this is the picture of what that cartoon would look like if we physically look at it, what we've been taking on trust. And so, not surprisingly, it's all explained by the form of this capillary pressure versus saturation curve, which originally here is for 2 phases, and kind of here is really for 3 phases, because we've added that extra component to it. So at least it gives us validation of what we'd expect to see in situ. So how do we get these magnitudes of saturations? Well, I guess you could do it in a fish tank, an aquarium, and look at the saturations as they develop. The other way you could do it is you could also look at the pressures that you develop in the system. So this exact same experiment, but shown in kind of a different way, is described here. And I think it's basically the same experiment. But instead of plotting it in terms of saturations with depth, what we're plotting it is in terms of pressures, fluid pressures, as you go down with depth. And so if you imagine within this column that we have here, that you had some instrumentation, so that at each of these individual depths, you could measure the pressure of the fluid that you had in the system, and you could plot the pressure of that fluid with its elevation, then the figures that you'd get would exactly be the ones that you see here. And so these are the instruments. They're tensiometers. They measure the tension, the tensile stress within the fluid, less than the cavitation stress at these different levels, T1 through 6. and they plot them versus gauge pressure. So this is atmospheric pressure here, which is 0, and this would be in centimeters of water. So 20 centimeters, 40 centimeters, 60 centimeters, just over half a meter, in terms of the height of a column of water. And what we know is that the definition of the water table is where the pressure is atmospheric. So by definition, if you have these results for these different tensiometers and you draw a curve through them, wherever it hits this line here, by definition, is the water table. So this, by definition, is the water table that I always identify this. This here is what we know as dz dp, right? And we've drawn it many times before, right? So you can think of this as just pressure change with elevation, and we know that this is equal to the unit weight of the fluid, in this case water, rho g. And we know that as we go across the water table, we can just extend that in tension. So this is at 0 pressure, this is at a compressive pressure, and this is at a tensile pressure. So it's less than atmospheric, it's tensile. And so we're going to do exactly the same as we did before. We're going to let some stuff wash down through here and see what it does. So this is 0 minutes. I think it's the same example, so this is 120 minutes. That's just done, not 1, 2, 3, 4, but 1, 2, 3, 4. So this is the tongue of oil as it hits. Perhaps it isn't 120 minutes, but some other time. So this is the tongue of oil. It's sitting on top of the water table. The water table was at this depth here. What it's done is it's moved it up. So this is now the new water table from here to here. Bless you. And by definition, it's where the pressure of the water is atmospheric. So that defines the water table. So these are the pressures that have changed in response. I guess what's happened is that it's loaded above the water table and compressed things. So it's increased all of these pressures towards the right, which is giving this. And you see two things. You see a water table. Again, we're just getting a physical feel for what's going on. And the other thing I guess we could call is an oil table. And so in the same way as the water table, by definition, is where the water pressure is atmospheric, that elevation, the location where the oil pressure is atmospheric is this location, and it defines a water table below which would be saturated in oil if we have it. And there's a very good reason for us wanting to know that. If we allow time to continue, then what happens is that this nose, which is here, that hasn't gone above 0 pressure, develops so that it goes above 0 pressure. And ultimately, as we allow it to reach equilibrium, then we have these conditions where this is the pressure within the oil. And was it blue, I guess, for the water? And this is the pressure within the water. And so, and this would be a demarcation between them. And so this would be the oil, whoops. This would be the oil table. And this would be the water table. And this has some ramifications for what we'll deal with. And so this has merely noted the fact that it's driven up the pressures in the fluid. It's rearranged the water table. It's actually brought the water table up from being at a depth of something like 50 centimeters above zero to something like 80 centimeters by zero, by basically taking the fluid that was present within the pores at partial saturation and pushing it down into the fluid which is present at the water table elevation to elevate the water table. And so this is zero pressure, this is zero pressure, represents the oil and water tables. This is a compressive pressure because as you're going down within this, I suppose the gradient of this, if we wanted to be really fancy, we can imagine that the gradient of this would be rho non-wetting fluid times G. And in this particular part here, this gradient of this curve would be given by rho wetting fluid times G equals unit weight. And so by definition, you can't really see it here, they look like they're parallel, but you'd expect that this one, the green one, should be closer to the vertical, right? If air, which has a low density, is almost vertical, and water, which is more dense, is canted over, then maybe gasoline, what is it, 600 kilograms per cubic meter versus 1,000 for water, would be partway between air and water. So this gradient here should be more vertical than this one. Imperceptible in this particular figure. Okay? And so we're interested in that because it makes some difference to what happens in the subsurface. So we've said before that we might like to, if we come upon a site where we have a puddle of gasoline sitting on top of water, we might like to know how much volume of that is present in situ because we're going to have to remove it. And so we don't know how much volume. We probably are not going to have a whole bunch of fancy instrumentation that allows us to build the pressure profile as we go down through this. We'll probably have a single borehole, and that borehole might go down through this. And in this borehole, we'd hope to be able to look to see what the different fluids are within this borehole. And what we would do is we would drill, let me find something online. Bizarre, always bizarre news, so what would we do without Google in these days? Perfect. Maybe even better. Videos. Should always be careful, I guess, in putting stuff on. Not rocket science. So all it is to measure the level of water, drop something down a well on a cord that has measurement of length, and you wait for it to hit water. And you have some kind of sensor on the bottom to be able to light a light bulb. So all it is 2 cords of wire, connector, water. The water is conductive. It makes a connection between the circuit, which is this central probe, and the material around it. Think of just 2 pieces of wire to get a circuit turned up. When it hits the water, it lights a light on at the surface, and you know how deep you are. So water level indicators are what we can use. We can also get fancy in that these can also pick out different resistivities to represent the transition from air into water as you go into or air into oil as you go into a fluid in the top of the borehole, and as you go from oil into water below it, it can also pick out that interface. So typically the only information you have is 2 elevations within a well, the top of the first liquid you hit, which would be oil, and the interface between the oil and the water below that, which you can pick out by this little handy instrument. And so in doing that, you could imagine that you'd like to be able to figure out exactly what this height is of the oil that sits supernatant on top of the water within this aquifer. And so we can do a very simple analysis to look at what that might look like. And it follows this idea here. So the oil is going to sit in this very high saturation lens. We're going to drill a hole through it. The capillary forces keep the stuff present within that lens and give it that particular shape. But as soon as you cut this hole through it, all of a sudden, instead of being held here by the very small pore spaces that keep it from going down, it's going to empty into this borehole and just fill up the borehole. And so what you'd imagine is that the profile that you might get would correspond to this geometry that we just looked like in the soil column, which would have the height of the oil present here, which is congruent with the height of the oil in the aquifer. But the bottom of the oil that we have here wouldn't necessarily correspond with the bottom of the oil that's present in the aquifer. And so this is the measurement we have in this vertical hole, but this is the measurement we want to figure out because it represents our system. So how do we rationalize that? We know that we have a water table which sits at atmospheric pressure. We know that we have the top of the fluid in the oil that sits at some atmospheric pressure also. And so what we could do is we could look at the balance of forces that we have that sit in the bottom of this well. And that balance of forces will be the pressure due to the oil that sits above it. And so we can calculate what the pressure of the oil is that sits here. If this is the height of the oil, which is T, then the unit weight of that multiplied by T gives us this term here. Right? These two terms here are gamma oil times its thickness. So unit weight times the thickness, P0. But the pressure here isn't has to be the same as that, but we can also get that by looking at what it is in the aquifer. So we know at the water table, by definition, at this point here, the pressure is 0, atmospheric. And so what we could do is we could draw a pressure versus depth behavior that looks like this. This is pressure, this is depth, this is 0 at this point here. And so if we want to get the pressure at any other particular point here, this is just going to be the pressure in the water is just going to be the unit weight of the water times the height W, which is rho W, gravity, and W, which is exactly the same as this. They have to be equivalent to each other. And so if we make them equivalent to each other and rearrange it, we end up with the term in the box. And so what we think we can measure the first liquid interface, oil, beep, or the light goes on. It goes down through that. It senses the next one, different conductivity, water versus oil. It goes beep. So you can measure both this depth and this height, absolute. If you subtract this one from it, you get T. And so if we know T, we know the densities of the two fluids, then by definition we have the magnitude of the thickness of the water. And if we have the magnitude of the thickness of the water, what we really want is going to be the height of the green stuff, which is this, which is equal to T minus W. Straightforward, right? So it relies on this idea that we have this tongue of oil going down. It makes a water table and an oil table. We want to figure out exactly what the real height of it is in the reservoir aquifer. We can only get the magnitude in the borehole, which is not the same as in the aquifer. We have to correct for it. And so if we can correct for it, we can always calculate what this is, because we know what W is just by the ratio of these two densities. and the thickness that we measure in the field. And so the utility of that is that we like to be able to figure out exactly how much stuff is present within our reservoir. And so the easy way to do that, aquifer reservoir. So we can calculate how thick the oil is. If we know that thickness and if we know the area of the reservoir and its porosity, this would be the volume of the voids that are filled within our aquifer. If we know the saturation that's present within this portion of the aquifer also, we can multiply this void volume by the saturation, and we immediately have the amount of fluids that's present. And so if we want to calculate the volume of product that's present within our system, so this is the volume of oil. It's something like the plan view area of the contaminated lens as you look down on it. It's which is this thickness. The porosity is the void space that's included in that volume. So this would be the volume of the aquifer that's that we can get in the system, if we draw it on these charts, would be if this, so would be this, right? Let me draw it up. So this would be, what's this? This is the irreducible saturation of water. This is the irreducible saturation of air. And this is the maximum saturation that we can get between that, and this is the saturation of oil. And so if you want to calculate what saturation of oil would be, it's just a geometric magnitude. And it's going to be 1, which is this whole distance across here, minus this amount, this, yeah, I'm not doing that very well. This, let me relabel this. Oh yeah, I guess that was right. Yeah, so this is the irreducible saturation of water. The 0 is the irreducible, minus the irreducible saturation of air. This is the amount of air that you can't get out of the system. It's going to be present here. This amount here. This is the amount of water you can't get out of the system. And by definition, the sum of all three have to add up to 1. And so we're just writing the fact that S water plus S oil plus S air have to equal 1, and so if we rearrange that, we end up with this. And so all this is making the point is that if we do this calculation, what we can pull out of this is the volume of fluid that we can get out, the area of the lens, the height of the lens multiplied by its porosity, and then the saturation that's filled with oil. I guess if we wanted to, we could also subtract a part here off, which is the saturation of air. If we remove this, that represents that. So it's just a geometric feature. If we looked at this in what it physically looks like in the subsurface, and we looked at combining what the profile would look like, then we'd expect it to look something like this figure here. So this is the water table. This is going up from the water table to the surface. And these are the saturations that we'd expect to see. This is the lens. So if we drew this out here, this lens here is what would look like this part here. This is the lens. Above this, we have an amount of residual water that's present everywhere in the system. Can't get this out. This is a bubble of the water that's present on the grain boundaries. As you go close to the water table, the gasoline's sitting on top, so it takes up this volume, which is basically this. Ignore these other curves for the moment. And as we go above the oil table, then it backs off so that the individual components are some residual water, ultimately residual oil as you get here, and a large amount of air that's in the system. So a three-phase system. For this particular calculation here, what we're assuming is that this saturation looks like this. In other words, this height here is what we've called T minus W. It has an area to it, and that this saturation here is equal to, again, it's a bit of a blunt instrument. This saturation here is equal to 1 minus the irreducible saturation of the wetting fluid. In this particular case, we've ignored the oil. And that if we multiply this effective saturation by the height of the thing multiplied by its cross-sectional area, which is this here, and we multiply it by the porosity, then we end up with the amount of volume. So, I'm not sure I did a very good explanation of that, but hey, that might be par for the course in everything I say these days. Okay? So the bottom line is, but we can take measurements in the field. We have the spurious height of the water table, which we'll measure in the well. We have to correct for that, which is this term here. And once we've corrected for that, we can figure out how much stuff is present in the subsurface. In reality, it won't quite look like this, because the capillary pressure curves will suggest that it has this form here that has these different saturations. So it actually might look a bit like this. But if you take this part here and you add it onto this part here, then you basically get this prismatic plug. So it's a simplification. So if you really want to do a rigorous job and use these distributions of capillary pressure versus saturation to get the true distribution of the product in situ that conforms to the stuff that I've just erased, in other words, conforms to this profile that we see here, then you can do an analysis for about 5 pages and you can get that exactly, and it doesn't really matter, and we won't do it. But the bottom line is you could do it to get a more correct, a more rigorous solution to exactly what it might be, but that's probably more than we need to do in this class. The other thing that you might imagine could happen with this is if you have stuff sitting within the aquifer that is buoyed on the top of the water table. So this is our lens here of fluid that's sitting as a lens that sits on the water table. Then if, for instance, the water table moves down seasonally, as you see from one to the other, then you could imagine that this lens would do 2 things. It has to follow the water table, because that's the only thing that's buoying it up. And as it moves down, you could imagine that it might want to spread a little bit laterally. And if it did that, you'd end up with it moving with here, and it would end up smearing as you go down from here all the way through the aquifer. So this smeared zone that you'd get would be a function of it moving vertically downwards. It would follow the water table. It might move a bit further outwards from this point. And then if that process is reversed, this would then carry the buoyed lens back up with it, just like in a swimming pool, and it would end up sitting back on top of the water table as it's moved up to the surface. So you can imagine that anomalously you'd end up with this portions, what originally was in our chimney before is present at these relatively low residual saturations below. And if you look at what the saturation versus depth column might look like as you did this, it would kind of mirror what we expect. So if we use the same colors as before, I can't remember what the colors were. Red was for water, I think. This would be the saturation of water. This would be the saturation of oil. And was it black? I can't remember. This is the saturation of air. And so this is oil. And so again, you see, if you look at this big saturation at this point here is kind of not going to work, I guess. I've gone outside my, I can do that, I guess. This would be the lens, which is sitting at the bottom of here. This would be the column, which has residual saturation, and then all below here, and actually out to the side because of this idea here, much further out than the column, would be parts that are residual saturation as well. So residual saturation, and the lens sitting here that gets moved up and down. Okay. So what kind of behavior do we get if we look at DNAPLs, denser than water? Well, you can imagine, again, if we look at this figure here, that we'd like to have, when we go in to measure these things in the borehole, which is the only access we have to the aquifer, is that we end up with some behavior, and we like to know if that behavior is true. And so if we look at what these would look like as you go from the ground surface, we've said that you spill it, you get this stuff going down and down, and it would maybe go down until it reaches a capillary barrier. And at that capillary barrier, you'd expect it to pool as a lens. It won't depress the barrier because it just sit on top of it. And so we'd have a lens at relatively high saturation that exists below this, and this would be this chimney which would be present at residual saturations. If we add some more in the surface, then you could imagine that this lens would get progressively larger and bigger as it gets here. And if you look at what that would look like if you could look at saturations in the column, then this is what at the capillary barrier, which we've drawn here, then the DNAPL saturation would be something like this. Do all the way across, maybe this. This would be water. We use blue, I think, right below. This is the border that we can't get out of the pores. And this is a lens. So the lens kind of goes up here. So I guess in this particular case, the lens would be up to this point here. And then above this, saturation slowly diminish of the oil as you get up to residual saturation, which makes up this chimney. And so this looks like this. So what we'd like to be able to do is to be able to figure out exactly where this zone exists here. And so we could imagine doing two things. What happens if this is the first borehole that we drill and we get down to here? Okay, we think the level of the stuff comes up to this height here. What happens if we then extend the drill hole so it goes down a bit deeper? Well, if it went down deeper, it would also just take in stuff from the side, which would flow in, and it would fill it up, and it would fill it up all the way down. And if we went down here, it would fill it up all the way down here as well. So if we're taking the level in here, we might think that the thickness of this might be all the way down here, but it truly isn't. because we've said that there's a capillary barrier that exists here. So that's the first thing that we have to be aware of, that the field information might lie because this was suggesting that it's really thick, but in reality it's not. So that's the one thing that we've got to be aware of in doing that. And we have to figure that out somehow. The second is that this height that it fills the well bore up to should be the same in both of these, and it should correspond with where, somewhere in here between this lens thickness and where it goes back to background residual saturation, somewhere within this zone would be where we'd expect to find this particular interface, the oil table if you like. And we're not quite sure exactly where. Maybe we could assume it's where it goes to residual, maybe not. But at least here we can figure exactly what this out is by measuring in the borehole. And as we go up in the column, just as we figured out in the case of LNAPL, the distribution of water, oil, and air in these particular cases, we can figure out exactly what that distribution might be here. We'd have air, we'd have residual oil in this particular place here. So this would be oil at residual magnitudes. This would be water at residual magnitudes, and this would be air. And you can imagine what these would look like as you go down. The other thing that you could do in the 2 seconds we have left is you could think of this distribution in the subsurface to a denser than water non-aqueous phase liquid as something that responds to the capillary pressure versus saturation curve. And so if you think of this as zero pressure and this is a very big pressure, then this particular capillary pressure curve here you'd imagine corresponds to quite big pore diameters because it can get in at very low pressure, right? So in other words, this is a low pressure and it can saturate it with this NAPL at that very low pressure. This other one is a very high pressure that you've got to overcome. If I write these curved things just as single steps. So this is low permeability and this would be high permeability. I don't want to have these. I want to get rid of this, what I just drew. And so exactly the same as the annotation here. And so you could imagine that as a function of these different saturation versus capillary pressure curves, they would make different distributions of saturation just as you have here. And so you could imagine that in the case of high entry pressures, that with high permeability material, you'd expect to get the NAPL coming up much higher within the column than you would within the low permeability one. So if I draw the saturated zones here as red, so this is NAPL all the way up to this case, which would conform to this particular case, and it's the NAPL at the bottom here, which is in this particular case due to the distribution of having to have a high capillary pressure to overcome to be able to get it at this region here. Here it can fill it up all the way at high saturations because the entry pressures are relatively low, and at higher in the column you're at a lower entry pressure, and it just means you can top it up further up because the entry pressures are lower. And so it's just a continuation, if you like, of this idea on the previous slide that the capillary pressure versus saturation curves, their form, say something about what the lens will look like in this particular case. In here, at low entry pressures, the lens can be very thick. Here, at very high entry pressures, you have to get a very high entry pressure for it to overcome it, and therefore you can't sustain these high saturations higher in the water column. That's it, I think. The one last thing, I guess, is to think about this figure here, is that if you don't hit a capillary pressure barrier that stops the stuff going, there's no reason that this stuff can't just keep on going almost indefinitely. And so it's only controlled by the presence of low permeability layers that are present within the system.